This is Dr. Kavita Singh, Associate Professor in Department of Civil Engineering in Institute of Aeronautical Engineering. So today we are going to discuss a topic called as Vector Data Model in GIS. So if you remember, in the previous lecture we have discussed about raster data model. So there are two types of data model in GIS. One is raster, one is vector. So raster data model is the representation of the data in the form of a grid format, and we have also discussed about the different types of data models like grid model, in-grid model, map model. So now today we are going to discuss about the vector data model. So in this data model we have two types of data model, that is spaghetti model and topological model. So how it works and which type of model is useful for the any kind of project works. So let us discuss this topic today. So before we enter to this topic, let us discuss what are the contents we are going to discuss today. So vector GIS model, types of vector data model, spaghetti model, topological model, advantages of raster and vector, disadvantages of raster and vector. So this all we are going to learn today. So first of all, what is vector GIS model? So if you remember, there are two types of data in GIS. Okay, so that GIS is spatial data. Okay, spatial data. In the spatial data, we are having two types of data. One is raster and other one is vector. So this two types of data we will just show in the form of a spatial data. So when we talk about the vector data or raster data, when we talk about the raster data, that is also spatial. Vector data is also spatial. So once we talk about raster data, so raster data is in the form of a satellites, aerial photos, or something like if we just see like scanned images. So these all images which are in the form of a grid format, that all comes under the raster. When you talk about vector, vector is a representation of the world, of the real world in the form of point, line and polygon. Okay, point, line and polygon. So vector data structures allow the representation of geographic space in a intuitive way of reminiscent of the familiar analog map, and the geographic space can be represented by the spatial location of items or attributes which are stored. So whatever are stored, it is represented. So in another file for later access, it shows how the different entity, namely points, line and areas, are represented in the form of a vector data. So it can be defined by the coordinate geometry. So which type of entity it is we are going to use, it is defined by the coordinate geometry. So like the raster spatial data model, there are many potential vector data models that can be used to store the geometric representation of entities in the computer system. So point is the simplest spatial entity. So we have three entities. One is point, one is line, other one is polygon. So this is a single entity. Okay, single entity, and it is having a spatial, and it is the simplest entity too. So that can be represented in the vector world with the topology. So a point requires to be topologically correct. It requires to be topologically correct. So point requires to be topologically correct. Topologically correct means the point should have x and y coordinate to a location. Okay. So correct with the respect of geographic reference. What is geographic reference? When you are assigning the location, that is latitude and longitude. Latitude and longitude. So this we are able to say about the geographical reference system, which locates it with respect to other spatial entities. So to have a topology, a line entity, topology means it's a topological, all the errors, if it is present in the point, line and polygon, to correct that errors. So to build all type of errors is called as topology, and to have topology, a line entity must consist of an ordered set of points, a locus of number points known as arc, segment or chain. So with a defined start and the end points and nodes. So if you remember in the digitalization process in the previous lectures, we have just learned about digitalization, that it is about the points, the arc and the segment. So this is the vertex. When you click like this, it will form an arc like this with the different segments. So when you want to make a polygon, you have to complete the segments, right? So if you want to make a line, it is the starting point and this is the end point. So line is formed. So if you want to make a point, just you put a point here. So that all known as this arc, segment or chain with a defined start and the endpoint nodes. So the simplest vector data structure that can be used to reproduce the geographical image in the computer is a file containing x and y coordinate pairs. So that represents the location and individual point features. Such a vector data structure for a car park. For example, here we have a vector data structure for a car park near the Hussain Sagar Lake in Hyderabad. So if you take this vector data structure example, now how a closed ring of coordinate pairs defines the boundary and the polygon is clear. So for example, if you want to define suppose this is a car parking area here in Hussain Sagar Lake in Hyderabad. So if you want to define the boundaries, so we have to make a closed ring and pairs of coordinate which defines the boundary, and it is also called as polygons. So pairs of coordinates means one vertex we will put of x and y coordinate, the second x and y, okay, third x and y, fourth x and y. So different points we are putting here, x and y. So x and y is nothing but it is a latitude and longitude, because each location is having a x coordinate and the y coordinate. Okay, so this is x and y, and here x and y. So this boundary we can just define with a coordinate pairs which will make a closed ring of coordinate pairs, and the limitations of simple vector data structure start emerging when more complex spatial entities are considered. Now there are two types of vector data model in GIS. So what are the two types of vector data model in GIS? We have two types of model, that is spaghetti model and topological model. So how the vector data is represented, how we can differ it from the raster is, like for example raster we represented in the form of the grid. Okay, so here these are the grids and where we can represent a point. So if you want to represent a point, we will just cover one grid. If you want to represent a line is represented with the covered with different grids. Okay, so this is line, and later polygons. Here is the polygon, so which is represented like this. Same thing if you want to represent it in the form of point line polygon. So in vector, this is raster. Okay, so in vector we will just show this is a point and this is a line and this is a polygon. So simplest way we can just show it like this. So this will become a vector. So in this vector we have two types of models again, spaghetti model and topological model. So let us understand what is spaghetti model and the topological model. So there are two types of models. Spaghetti model is a model which is having an individual entity, right? Individual entity in sense, if point is there, this is an individual entity. If the line is there, this is one line, this is the other line. And if polygon is there, this is one polygon, the other polygon is like this. So all are the single entities. So it is not crossing this line. Okay, so if it is not crossing this line, or this line is not common to this line, so it is not, one entity is not crossing to the other. So that's why it is called as spaghetti model. Spaghetti model is the individual entity which will not it is not in contact with the other entity. So that is called as spaghetti model. Topological model is always a complex model. In the topological model you may find, suppose this is your polygon. So in a polygon you may have the other polygon, you may have the other polygon. Okay, one more polygon in polygon. So there are many polygons here. So this polygon will be for example, this is one polygon, this is polygon 1, polygon 2. So this line will be common to polygon 1 and polygon 2. So this is a complex model where you find that one line is common to the other entity boundary. So spaghetti model, the simplest vector data structure that can be used to reproduce a geographical image in the computer is a file containing XY coordinate pairs that represents the location and individual point features. So it is a simplest vector data structure that can be used to reproduce a geographical image. So simplest model is a spaghetti model, and it will be represented individually in the form of XY coordinate pairs. Okay, so each graphic object can be represented with a piece of spaghetti. Each piece of spaghetti acts as a single entity. So each piece of spaghetti is what? Single entity here. Line is a spaghetti and polygon. So each one will be showing as a single entity. It is not mixing with the other one. So the shortest spaghetti can be represented as point. So what is the shortest spaghetti means? You have only one single point having x and y. If you want to show lines, so it will having 1 point, 2 point, 3 point, 4 point, 5 points with series of x and y coordinates. Okay, series of x and y coordinates. So that becomes a line. So point is having a shortest spaghetti which is having only a single. Now polygon is a series of spaghetti lines, like we close a polygon like this. So it will be having number of points with x and y coordinates. So that will be a complex one, and the simplest and the shortest one is a point. So that come together at a beginning and ending of surrounding areas from the area entity. Each entity is single logical record in the computer encoded as variable length strings and coordinate pairs. Let us assume that two polygons lie adjacent to each other, and other is the inner thematic coverage. So these two adjacent polygons must have separate pieces of spaghetti for adjacent sides. So for example, we have, this is one polygon, so this one is the other one. So each is having their own boundary. Here is having, this is one single, and the other one is also having a single. The other one is also having a single. So each of the polygon is having its own separate boundary. There is no boundary which is common to each other. So each is having a separate boundary adjacent sides. So that is no two adjacent polygons share the same string of spaghetti. So no polygons will share the same string of spaghetti. For example, this is polygon 1, 2 and 3. So it is not sharing this line with the other one. Okay, so it is having its separate four sides. Here also separate four sides, separate four sides. So if it is circle also, this is one circle. So it is having its own circle like this. So it is having its own different sides. So it is not making the common line to the each of the polygons. So that is no adjacent polygon shares the same string of spaghetti, right? So each side of polygon is uniquely defined by its own set of lines and coordinates. Uniquely defined means this is 1 and this is 2. So each set of polygon is uniquely defined. 1 side, 2 side, 3 side, 4 side. Now 1, 2, 3, 4. So each side is having unique ID, right? So this is one side is defined, this side is defined, this side is, all sides are defined together. So in this model of representing vector data, all spaghettis are recorded separately for polygons. But in the computer, they should have the same coordinates. So in the computer, they should have the same coordinates. They should not be with different coordinates. So it should have the same coordinates. Now here is the spaghetti model. Here is the example of spaghetti model, how it looks like. So when you want to show in the digital map, it looks like this. If you want to show in the analog map, it looks like this. Okay. Now here xy, you can see xy is the, what is xy here? Point. This is also xy is point. So it is represented in the digital form like this. It is represented in the digital form like this. Now you have a line and you have a polygon. So line you have here. So this is the line. Okay, this is the line. You can see here. So this line is having a string of points. So it's separate. It is not connecting to each other. Okay. So you have a polygon 25, 25. These are all separate polygons. It is not connecting to each other. If you see here 5 is xy single pair, 16 is string of xy coordinate pairs, and 25 is closed loop of xy coordinate pairs where first and last pairs are the same. Now 26, if you see here, closed loop of sharing coordinates with adjacent polygon to form a data structure. So this is how the spaghetti model looks like. It's a very simplest model and it's a very individual. Each side of each entity is having a single identity. So it is not combined with the other one. That is what this is called as a spaghetti model. Now topological model. So topological model, in order to use the data manipulation and analysis subsystem more efficiently and obtain the desired results. To allow advanced analytical techniques on GIS data and its systematic study in any project area. Much explicit spatial information to be created. So topological model is it's a complex model. It shows the complexity, like complexity in sense. One model is like this. For example, we have different polygons like this, So it is having 1, 2, 3, 4. So this polygon is sharing this line. Okay, this second polygon is sharing with third polygon. This line it is sharing, this line it is sharing. Now the third polygon is sharing this line with the other one, and the fourth polygon is sharing this line with the other one. So this is the fifth polygon. So if it want to share the other line, it can be shared with the other one. So to allow advanced analytical techniques on GIS data and its systematic study in any project area must explicit the spatial information to be created. So the topological data model incorporates solution to some of the frequently used operations in advanced GIS analytical techniques. Now this is done by the explicitly recording adjacency information into a basic logical entity. So in topological data structure, beginning and the ending when it contacts or intersects with the other line, or when there is a change in the direction of the line. So each line then has two sets of numbers. Each line is having two sets of number. That is a pair of coordinates. The pair of coordinate is x and y, and associated with the node number. So the node is the intersection of two or more lines. So what is a node? So suppose this is the polygon here. So this is one node, the other node, the third node, and if you are adding one more, this is the fourth node. So like the node is having a associated with the node number. So the node is intersection of two or more lines, and its number is used to refer to any line to which it is connected. So in addition, each line segment called a link has its own identification number that is used as a pointer to indicate the set of nodes. So these links also have identification codes that relate polygon numbers to see which two polygons are adjacent to each other along its length. So in fact, the left and right polygon are also stored explicitly so that even this tedious step is eliminated. So this design feature allows the computer to know the actual relationships among all its graphical paths. So to identify the spatial relationship contained in an analog map document. So the design feature allows the computer to know the actual relationship. What is the actual relationship between one polygon and the other polygon 1 and 2. So what is the actual relationship between 1 and 2? So it will help us to design the feature and allows the computer to know the actual relationship and its all graphical parts. To identify the spatial relationship contained in an analog map document. So the topological model available in GIS, it ensures, what it does, it ensures that no node or line segment is duplicated. Okay, remember in the topological model, no node line segment is duplicated. So that's what I was telling. This is 1, 2, 3, 4. 1, 2, 3, 4. So here you can see this is common line, this is common line, this is common line. So there is no two lines. If this is the line, there is no two lines. This is a common line. So duplication is not there. Okay, duplication is not there. So the line segment and nodes can be referenced to more than one polygon. It can be referenced to more than one polygon, and that all polygons can be adequately represented. All polygons can be adequately represented. First thing, there is no duplication, and the second thing is the line segment and nodes can be referenced to more than one polygon, and the third thing is that all polygons can be adequately represented. So this is how the topological vector data model looks like. So it's a very complex model. We can say it's a very complex model. Okay. Now if you observe here very clearly, you can say this is A1. Okay, this is A1. and the second one is A2, the third one is A3, and the fourth one is A4. So 1, 2, 3, 4, and this is A5. 5, 6, 7, 8. So total 8 polygons we have here. So 8 polygons, you will see that A1 is adjacent to A2. Okay, so A1 is adjacent to A2. Now this line is common. Which is the line? Line 15. This is node 1, node 1, node 2, node 3, node 4, node 4, and node 5 is this one, node 6, node 7, right? So how the node is decided here? Node 1. So one click, second click, third click, fourth click, fifth click, sixth one, and the seventh one, and it joins the node 1 again. So this is how the polygon is made. Now it is combined like this. So this is node 1, node 2, node 3, node 4, node 5, node 6, node 7. So 7 nodes it is created. Now with the 7 nodes, all the polygons are joined. Okay, here, right? So like this it is joined. So many polygons are created. So in this you can see we have total 8 polygons and we have 7 nodes. Now if you see the line 1, line 2, line 3, line 4, line 5, line 6. Where is the line 7 here? Line 7 here, and you have a line 8 here, line 9 here, line 10, 11, 12, 13, 14, 15. So these many lines are there. Now you see one thing. This polygon is node 1, node 7. Now polygon is from here to here. Line 6, line 7 and line 15 is one polygon. Now the other polygon is line 15, line 14, line 1. Now line 15 is common to A1 and A2 polygon. Now here line 14 is common to line 14 and line 13 is common to A3 and A polygon. Like this, it is a very complex model. There is no line which is duplicated. All are having a common line with common boundary for other polygons. So there is no chance of errors. So this type of polygon, this type of model is used to prepare maps. Okay, so this model is very important model and it is very useful for creating the different kinds of maps. Right, so this is topological and spaghetti model. So these are the two types of models. Spaghetti model is not too much useful in other types of creation of the maps. Nowadays, when you want to create a map, we can use this topological model for a complex situation where you can find a common boundary for each 2 or 3 polygons. Okay. Now, next, if you see the advantages, so we have certain advantages of raster and vector both. Okay, when you talk about raster and vector, so we have 2 advantages. You can see here raster advantage and vector. So what is the raster? It is a simple data structure. Okay, simple data structure means simply if you click a map or if you scan the map, it is converted to the raster. So it's the simplest one in the grid format, and same the way it provides, a vector provides a more compact data structure than the raster model. It provides a compact data structure and raster model provides very simple, right? So second advantage is overlay operation are easily and efficiently represented in the raster format. Now in vector, if you see in raster, if you see overlay operations are easily efficiently represented in raster format. High spatial variability is efficiently represented in raster format. The raster format is more or less required for efficient manipulation and enhancement of digital images. So this is a very simplest model. Easily we can overlay. The operations are very easy. The displaying the data is also very easy, and high spatial variability and efficiency is represented in the raster format, and the raster format is more or less required to efficient manipulation and enhancement of the digital images, whereas in vector model, if you see, it provides more compact data structure than the raster model. It provides efficient encoding of topology as a result of more efficiently implementation of operations that require topological information such as network analysis. Okay, the vector model is better situated to supporting graphics that closely approximate the hand-drawn maps. Okay, so vector model is closely suited to the supporting graphics and it is closely approximate hand-drawn maps. These are the few of the advantages. If you see, raster is the simplest one. Overlaying is also simple. Whereas when a vector advantages, it provides a compact data structure and than the raster model. And it provides the efficient encoding topology, as a result more efficient implementation of operations that require topological information. Moreover, we can just create our own maps as per our requirement based on the data provided by the raster. Okay. Now, if we talk about the disadvantages of raster and vector, so raster data structure is less compact, right? And it is topological relationships are more difficult to represent. So that is also one disadvantage. The output of graphics is less aesthetically pleasing because boundaries tend to have a blocky appearance rather than the smooth lines and hand-drawn and maps. This can be overcome by using a very large number of cells, but it may result in unacceptably large files. So file saving also, it has to take more space first of all, and the output graphics are aesthetically pleasing because boundaries tend to have a blocky appearance and topological relationships are more difficult in the raster data structure because it is directly captured by the data computer system and it is more complex. Vector disadvantage, if you see, it is more complex data structure than the simple raster. So complex data structure, as we have just seen, it has two types of data modeling vector. One is spaghetti, the other one is topological. So topological model is having a complex situation. It will just cover the areas with a very with a complex situation, like for example this two polygon 2 3 4 5, so common lines will be there. And for example we have two features here. For example, let us say this, we have a forest boundary. Okay, forest boundary. Now in the forest boundary, along with the forest boundary, there is attached agriculture. Okay, agriculture. So this line, it will be common to forest boundary and it will be common to agriculture. So it's a complex situation, but it will provide us this more data structure, and overlay operations are more difficult to implement here. So here the overlay operations are easy because already the data is georeferenced. And here the overlay operations are more difficult because until unless the data is georeferenced, it will not sometimes the data will not fit to its position. Okay, so more difficult implementation, and the representation of high spatial variability is inefficient. So the representation of high spatial variability is inefficient. Why inefficient? It is not efficiently represented because of the high spatial variability. So different variability in the spatial data will having the less efficiency in the representation. So manipulation and enhancement of digital images cannot be efficiently done in the vector domain. Like manipulation and enhancement of digital images, for example, raster is having all the images with the grid formats. Okay, so grid format means it has a already DN numbers are provided for each block. So it is having DN number 1, 2, 3, 4. So each one is having a DN number. So with the help of this DN number, the image enhancement is easy. Manipulation of enhancement of digital images are easy, but whereas in the vector data we cannot enhance the image because it's a very complex data structure and it has converted into a soft copy of the raster data. So enhancement of the image is not possible in this vector domain, whereas enhancement of the image is possible in the raster data. So this is one benefit in the raster, whereas in the disadvantage in the vector is we cannot enhance the image after the image is converted to the digital format, or the soft copy of the raster image. So these are few of the disadvantages. So we have many advantages and many disadvantages compared to the raster index vector. And these two data are studied together in GIS, and these two both are the spatial data which we study in GIS. So I hope you understood about the vector data model, types of model. Previous lecture we have studied about raster data model. Raster data we have studied grid, in-grid and map model. Now here we have studied in vector data model, spaghetti model and the topological model. So there are only two ways of representation of the data which we receive from the real world. So that data is represented in the form of either raster, either vector. So both are represented in the form of grid format or as the point, line and polygon. So that data is represented, and that further we can use it for our any kind of information if we required, or any useful information to be, any output we require from this data, we can just get it. So these are the disadvantages and advantages and models of raster and vector. Now these are the few references you can just go through. So for raster data model and vector data model, the reference you can just go through the M. Reddy remote sensing and GIS by VS publication for raster data model and vector data model. Okay, so these two things you can just find out, or later you can just find out this content. You can just go through to get more information about the different examples of raster and vector data model. Okay, and later you can just go through the Stan Chang GIS TMH publications and corporation book for getting the information about the GIS applications or GIS of raster and vector representation of how the data is represented in from real world to the map. Okay, from 3D to 2D system. We can just go through this book and you can get the information about it. So I hope you understood about the raster and vector data models. So these models are utilized in GIS, and these two are spatial data, because spatial data is only required in GIS to work with. Along with the spatial data, we need the non-spatial information to work with GIS. So next lecture we'll be learning the different types of map projections and all in the coming lectures. So that's all for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.